Hello, grade 9. This is lesson number 9, molecular structure and materials. Before we get started on today's lesson, I want to rewind a little bit to lesson number 8, which was our neutralization lab. Now, this was posted for you guys on Wednesday, even though Wednesday is not a day we do science normally, but it's not due until Thursday. And the reason I posted it is to give people a little bit more flexibility in how they manage their time. Okay, so it wasn't posted, and then you have to have this done even though it's not a science day thing. It was more to give you more options because we had 2 things left to do this week to finish the unit. That would be lesson number 8, the lab, and then lesson number 9. So when you do the lab and you upload it, the other thing you have to do as well, based on what you learned from that lab, is the third big idea. So our third big idea here is how is a categorization of chemical reactions linked to bonding types. So that's really also from our previous lessons, talking about the different reaction types. We talked about simple and complex chemical reactions. It's the 3 previous lessons all kind of tied together. So how does bonding types connected to reaction types? Okay, so that's big idea number 3. And then of course for that lesson you should be uploading your virtual lab assignment, and it's summative, it's being assessed, as well as big idea number 3. Then lesson number 9 we're doing now. This is the actual screencast lesson. This is the last lesson for this year. This is your last grade 9 science lesson, guys. It has been quite the year. You've done 7 units. So we've had our ups and downs for sure, but you are almost done. So pat yourself in the back, take a deep breath, and keep on moving forward. So we're talking about molecular structure and materials today. So here's your template, molecular structure materials, the lesson title. We have a section on material science, what that is, the applications powers of metals, ceramics, and polymers. We're only doing 3 examples. We're connecting them to what we've learned already so far in this unit. So take a minute, pause the video, and draw your template. Your last template for the year. Crazy. And that will lead us to big idea number 4. So here's our last big idea. How does the nature of the bonding within a material determine its properties and uses? So that's really big from today's lesson. And as you already know, your final exam is based exclusively on big ideas. So it's really important you do a really good job answering these big idea questions, because that is what your final exam will be based on. Okay, so let's start talking about material science here. So material science is the scientific study of the properties and applications of materials. This is really, sorry guys, where engineering and science come together. So science is the theory of all these things, how the world works around us, and then engineering is applying that theory to solve problems in the world around us. So material science is just a research component that will then be applied by engineers. It's very much tied with engineering. So why we put this, material science, why is our last lesson in our chemistry unit about material science? What's the connection here about chemical bonding? Well, the number one thing that determines the properties of a material is the bonds. We talked about different bonding types, 4 different types of bonds, and 2 different types of bonds, and how they really affect the different kinds of the properties of the compounds that are made of those bonds. So we're looking at an example here, how this is applied. So when engineers want to develop something new, such as smartphone glass, they have to start with the function they're trying to meet, and then think about the materials that have the properties that could allow them for that function, and then test those materials. So for example, here's smartphone glass. It's actually glass. It's quite flexible. So the problem would be the engineering process. What is the problem? What is the thing we're trying to figure out? We're trying to figure out a piece of glass for a cell phone that is thin enough you can use it for a touch screen, but strong and sturdy and flexible. Get possible solutions, different materials that have the properties that might allow it to work, and then you're going to test them, evaluate them, and then further narrow down your problem and narrow down your properties of your different materials, and then keep going again and again and again until you have a final solution. And as you know from the way cell phones keep changing all the time, there's always improvement. They're always looking for a slightly better version of things. So if smartphone glass has to be flexible, but it also has to be strong enough to be resistant to cracks. You don't want the glass to just be breaking all the time. I know I'm lucky enough to never have cracked my phone screen, knocking on wood right now, but I know people who have, and it's really important. If that screen breaks, it really ruins your phone. And phones are expensive, so it's important that they have the right materials, the right properties to do the job. So if we understand the properties of materials, to do that, you have to really understand the molecular and atomic structure of the materials. So I have a friend I studied with in university, my undergrad, and she is now a chemical engineer. So we took a lot of our chemistry and physics and math, science classes together, and I pursued into a degree in biology, and she pursued into a degree in chemical engineering. But we both sort of have the same kind of fundamental thing about what is chemistry, what is physics, how does matter react in the universe, because that's a fundamental part for both things. Okay, the atomic structure and the bonds is at the foundation of all the properties of matter in the world. So we already talked about ionic and molecular compounds. Do you remember the properties? If you don't, there's a picture here that will remind you. So we have ionic bonds, which is the positive-negative attraction between the different atoms, different ions. When makes a very strong bond. And so it's a good conductor because the charge, both of heat and electricity, when it's dissolved in a liquid, it's a very strong bond. They have a high melting point, high boiling point because it's a strong bond, and they're usually solids. And then in molecular compounds, it's pretty much the opposite. So melting point and boiling point are going to be low. This is a weak bond. They're not good conductors in water, and they're not soluble in water, whereas ionic compounds are soluble in water, as you saw with the neutralization lab, where you have the OH dissolving in water from that salt, and the salt ions staying separated in the water for the most part, despite the fact that they did form a compound. What about metals? We talked about metallic bonding. The powers of metals for metallic bonding, can you remember that? The fact that they have these delocalized electrons kind of floating between different atoms, and that allows them to be very malleable. You can bend metals without breaking them. They're really good conductors of heat electricity, and they're really ductile. You can pull them into wire really easily because this flexibility comes from the fact that the bonds are weak and flexible between multiple atoms. It's kind of floating around, electrons help hold it all together. So we're going to start by talking about metals. So metals are a really ancient example of material science in humanity. We've been using certain metals for very specific purposes for about as early as 10,000 years ago. And the first metal to be used by humans was copper, but people extracted it and refined it, not 100% pure, but pretty darn close. And they used it mostly for jewelry and ornamentation. So in the image, the top image here, these are copper rings. You can tell they're kind of gone green a little bit from the reaction, the oxidation reaction. And those are from the Aztec site they were found. So people have been doing that for a long time. And then bronze is where you mix copper and tin, those two elements, and together they become a new property, a new material, bronze, which is much more harder and much more durable. It makes really good weapons. There's a whole period of human history called the Bronze Age, where bronze was discovered, and it really changed civilization because now we have these really strong weapons, like these daggers, this picture, that really changed how people interact with each other, and hunting, that kind of stuff as well. So those are two examples of use of metals, jewelry and weapons. How many other ones can you think of, uses of metals? Can you think of more than 10? Well, here are some examples. We often use them for structural support, for like steel beams in bridges and buildings. Steel is really good, it's a very, very strong metal alloy. They're really good conductors. Metals are good conductors because of those floating around electrons. So we use them in electrical wires. Oftentimes we use copper, which is a good conductor, but it's not the best conductor. Gold is actually better, but it's just so expensive, and copper works just fine. So we use copper most of the time. Metals also very often used in medical use. So we have, here's a scalpel, scissors, different surgeon tools. I was looking for pictures and I almost put the dentist tools, but they kind of freaked me out, like the big, like, pull your tooth out tool, and I was like, no, I do not like the dentist guys. Anyway, The stainless steel has a good property where it's easy to make it very smooth. It's really resistant to high temperatures, so it's really easy to sterilize those tools. They're durable and they can be sterilized really easily to keep them clean. And then, of course, there's a property of alloys where we can mix different metals together, like bronze and steel are both examples of alloys. And they have different properties than the pure metals. So bronze has different properties than copper or tin, and they usually are stronger than the individual element metals. And it's just all these properties are caused by the bonds, by those strong metallic bonds with the delocalized electrons. They're strong but flexible and makes them really ideal for all these various uses. Okay, the next group are called ceramics. So ceramics are really very stable, and a lot of examples of ceramics still exist today that have been used for thousands of years. They're not a new idea using ceramics. And it's not just ceramic as in like pottery or dishes. There's many other types of things that are ceramics. Concrete is an example of a ceramic. And there's some really amazing, really long-lasting structures made of concrete. The Colosseum is one of those. If you've ever been to the Colosseum, it's really impressive. The size of it is kind of staggering. If you look at this image here, those are people at the bottom. It's very huge, and was built, I'm not going to guess at how many hundreds of years ago, a long time ago, and it's still standing to this day. So ceramics are very strong materials. And they're made from bonded metal and non-metal atoms, but they don't contain a lot of carbon, and they're usually made by mixing different earth materials in powder usually, and then we add water and heat to help cement the bonds. So for example, concrete. You make concrete by taking cement, sand, and stone or gravel, combining them together, and then you mix with water. And the water causes the materials to get close to each other, and then when the water evaporates with heat, it creates the bonds between the different materials. So when we're making concrete, like at the Colosseum, you pour concrete, you're not putting it in a kiln like you would a piece of pottery. Instead, what you're doing is you're letting the sun dry it, and the heat from the sun causes it to change form and harden. Okay, whereas you're making pottery, if you ever had a chance to work in pottery in an art class, you can make things. They make really beautiful pottery in Morocco. You make it on the wheel, or you make it by hand, and then you put it in the kiln, makes it really hot, and allows it to become hard within hours instead of days. And because of the nature of clay, the bonds formed are quite strong, but it's very malleable, which is not the case. You can't take a bunch of concrete and then mix it together to make a shape, right? You had to pour it into a form that's too liquidy. So clay is a different ceramic that has different properties, but still use the same thing. You use a little bit of water and heat to make the bonds between the different materials, different components. So I want you to draw these ones. Make sure you put the numbers 1, 2, 3, 4, okay, because it's really important. The blue here represent electrons, okay, in this one, in these two. So ceramics include, of course, concrete. It includes pottery, but it also includes glass as a ceramic, tile ceramic, bricks, porcelain, basically all the different earth materials that don't have metals or carbon, like wood, rubber, plastics. So there could be metallic elements in there, but it's not made of like a pure metal element. Okay, so be careful with the differentiation. And ceramic materials tend to have a mix of both ionic and covalent bonds, and they're really tend to be very organized in a three-dimensional kind of a structure. So how do you think those bonds, how do they change the properties of ceramics compared to metal? So in ceramics we have both ionic and covalent bonds, and in metals we have these metallic bonds. So which ones are stronger, and how will that change the properties? Well, we know the strongest bond type is ionic. It's that positive attraction is a very strong bond type, and then covalent are the next strongest, and the metallic are the next strongest. So we already have a much stronger bond holding these atoms together in a very organized way in ceramics. So image number 1 here, we're showing what happens with breaking. The first image here is a metal, and we talk about metal being very ductile. You can pull the metal apart and it'll come into a wire. Whereas if you have actually to pull a ceramic apart, try to stretch it, it's just going to break. Why would it break? Well, the bonds are so strong holding it together that the only way they can't lengthen, they can't stretch between them. So it ends up just either breaking or holding. It's a lot harder. If you pull on like a piece of pottery or some concrete, you don't have the strength unless you're like the Hulk to pull it apart and break it. But you can take a piece of metal, like some copper maybe, or some other very weaker metal, and you can pull it apart by hand, no problem at all. Kind of stretch it out. It's not a challenging thing to do. Okay, number 3, this is showing the metal, and this is showing little blue dots are the electrons moving between the different elements, the free electrons. And then number 4, this is a ceramic, and the blue are the electrons bonding the different atoms together. So this is about being a conductor versus an insulator. This is a really good conductor. We know metals are good conductors of electricity and of heat, where ceramics are good insulators. So remember, for my electricity stuff, insulators are ones where they don't allow heat or electricity to move through them very well. So for example, I know I have ceramic tile that I use as a trivet. So when I cook something actually hot, I put it down on the ceramic tile on my countertop, and it's not burning anything. Because stovetops are often ceramic materials, so they're really good insulators. Oftentimes you see old kind of wiring systems, they use glass or other kinds of ceramics to act as insulator on the wiring. All those kinds of things are good insulators because they don't have enough free electrons to allow electrons to flow between them. The electrons are all stuck in very strong covalent and ionic bonds. They're not free to roam around like they are in metallic bonds. Okay, so here's an example. Since there's a launch happening with NASA, tried to happen today, I just found out it didn't go today. Hopefully it'll go later on this week. So here's a list of the properties of ceramics. They have high melting points. They're resistant to heat. They have really great hardness, not hardness. Oh gosh. Last lesson, guys. Last one. Really good hardness and strength. They're very durable. They have a low electrical and thermal conductivity, so it's not much can move between different ceramics. It kind of stays in one place. And they are chemically inert. They don't react. So here's a spacecraft from NASA's the shuttle. Here's the nose region of it at the front. And these little white boxes, those are all ceramic tile. And here's a thruster. We have black ceramic tile down here. Slightly different ceramic versions because it's going to be much harder the thruster is than the nose. So why are ceramics ideal for spacecraft, for the exterior of a spacecraft? Well, the big thing is for the thruster region and the nose both, when they heat up, it's going to hold the heat on that point and not allow it to enter the spacecraft where the people are, where the fuel is, where all those things are. So the thruster is going to be really hot when it's burning, and the nose, or the whole thing, will be hot when it's re-entering Earth's atmosphere and hitting that friction and kind of burning up on re-entry. But the ceramic will heat up and be very, very heat resistant and strong, and it will not conduct that heat anywhere else within the space shuttle. Okay, the last one are polymers. So polymers are both synthetic and natural. So some synthetic polymers would be like plastic storage, like Tupperware, that kind of thing. Contact lenses are made of polymers, and if anybody gets wear contacts. And then we have natural polymers, like DNA is a polymer, spider silk is a polymer, proteins are polymers. They're all examples of natural polymers. And so plastics are polymers made of hydrocarbons. We're going to talk about hydrocarbons a little bit, and they're made of these chains of carbon and hydrogen, and the main source of those is fossil fuels. So when if you're trying to be more sustainable for the environment, it's not only about stopping using gas and coal and oil. If you stop using plastic, that also reduces fossil fuel waste. There's different structures of polymers, which, surprise, surprise, makes them have different properties. So here are the 4 main structures. You need to draw this, make sure you label them each one. So A, these are linear polymers, B are branch. We have some branches coming off the polymer here. C is a cross-link. We have linear, but with cross-links kind of between them, cross bridges between them. And D is a network, lots of branching here between them. So depending on what kind of chains you have in the polymer and how long those chains are, that will affect the properties of the polymer. So a great example of this are thermoplastics. So thermoplastics are plastics that will melt when you heat them up. They have really strong covalent bonds between the atoms, but it's a single chain. So it's a linear polymer like this. And the attraction between the chains are quite weak. So this is part of what allows them to melt because it's not as strong as an attraction because we have only bonds in the long chains. And the longer the chains are, the tougher the material is. So if you have a thermoplastic that you can boil and not melt, it's going to have a lot longer chain than one that will melt at a lower temperature. Okay, so we have microwave-proof plastics and plastic can't go in based on, that's a part of that is based on the length of the chains in the polymer. So let's try and apply this. So we're learning this whole lesson about bonding and properties and how they connect. Let's see if you guys can do this. So here are those 4 types again, and here's 4 descriptions of different polymers. I put an image of them here as well. And what you need to do is identify which one is which, okay? So low-density polyethylene, LDPE, is a flexible polymer with many subunits as side chains. So that's like this water bottle is made of LDPE. It's one you can press with your hand and kind of squeeze it and squirt the water out. So it's pretty flexible. Which kind of polymer is that? Number 2, epoxy adhesives like this one here. This is epoxy being poured. They're very strong and heat resistant, and these polymers have so many connections between chains, an entire sample could be one molecule. So which type of polymer do you think that one is? Synthetic rubber is strong and stable, so this car tire is made of synthetic rubber. And this polymer forms long chains with strong covalent bonds between the polymer chains. So which one is that? And number 4, nylon, like in this fishing net made of nylon, is strong with a high density and a high melting point. They have long polymer chains stacked closely together. So which one of these is that? Pause the video, write these examples down, take a guess. Which one do you think is which? But try and be logical. Each one is only there once, so you won't repeat any types. Okay, don't cheat. The next slide is the answer. Don't move to the next slide, next part of the video until you've done it yourself, okay? All right, so low density LPE is a branched one. We have many subunits, that's this one here, B. Epoxies are these networked ones, very, very strong. Cross-linked are the synthetic rubber, that would be C, and linear is nylon here. These chains are stacked, they're not bonded. And so these are all polymers, but very different properties, very different things. When resin hardens, it's like a rock. It's really, really, really hard. You can put really hot things on it. It's really hard to scratch it. It's very, very strong. One of my friends pours resin for artwork, and it's really tricky to control, and once it hardens, you're not undoing it. What you've done is done. Okay, that's the end. That's our last lesson, guys. So your homework is to upload a copy of your notes and study for your test. That's it. Hopefully you enjoyed this chemistry unit and you enjoyed the year overall. I know the last couple months have been rough for everybody, but you guys are almost done. We can see the light of summer vacation right there. Just put your nose to the grindstone and get through the next 2 weeks, 2.5 weeks, and then we will be done. You can do it, guys. Take care.